Hello students. Today we'll discuss on the second part of the design of compound column, the design of lacing. So what is lacing? If you want to see, the code has given a picture, good picture, and it is in page 49. These are the lacing members. You may provide double lacings also. These are provided in both the sides of the compound column. So if we want, we can provide either of these two or combination of batten and lacing system. So lacing gives us the opportunity to connect the two separate members to behave as a single member and also to reduce the slenderness ratio of the column. So the effective length become a small one and the slenderness ratio reduces, thus the load taking or compression taking capacity of the member decreases. So here on we will see that load on the lacing member, which is acting as an axial load on the column, is divided into two because we have provided lacing in two phases. So force per phase will be 1080 divided by 2 and the moment per phase will be 350 divided by 2. So now how much of this load will act on the lacing? So that is given in our code. So let us come to the relevant clause. It is mentioned in this clause 7.6.1.6.6.1. The lacing shall be proportioned to resist a total transverse shear Vt as any point of the member equal to at least 2.5% of the axial force in the member and shall be divided equally among the all transverse lacing system in parallel sides. So we have already divided the force in the parallel sides. It is divided by 2. Now we'll take that 2.5% of the load and also additional moments. So this is the problem where we have divided it and have mentioned the clause here also. 2.5% of 540 kilonewton, that is 13.5 kilonewton, and load on the lacing system from moment will be 175 per phase and it will be divided by 10. Why? Because if the length of the column is 10 and the moment is acting above, so we'll take the value of the plastic shear, that is the moment divided by the total length of the column will give the force acting transversely. So we have taken 175 divided by 10, the length of the column is equals to 17.5, and added this to find out the total load. It's coming as 31 kilonewton. So again we'll go to the code, to the clause, that the geometry is given also mentioned by the code here in clause 7.6.4. the angle of inclination. What should be the angle of inclination? This angle of inclination that is stipulated by the code. The lacing bar, whether in double or single system, shall be inclined at an angle not less than 40 degree nor more than 70 degree to the axis of built up member. So we may see here that code has mentioned to take angle of inclination within 40 to 70 degree. Here for convenience we have taken it as theta, we have assumed it as 45 degree. So what should be the length of this? The center to center distance, this one is known to us because we have already designed the column and it has been found to be 400 millimeter. So if I say that L cos theta will be equal to 400, so what should be L? If the inclined length is L, this one 400 divided by cos 45 will give you the length of the lacing. So it is coming as 565.68 millimeter. Now again, if you see the total force, that is 31 kilonewton, if it is acting like this horizontally, a part of this will be taken by this inclined member, or we'll say it will increase because this PL cos theta is equals to P. So how much should be PL? PL is equals to 31 by cos 45, that is equals to 43.84. I repeat here, PL, the load taking here, if I resolve it in horizontal direction, it will give PL cos theta, that will be equals to P. So what should be equals to P? It will be P by cos theta. PL equals to P by cos theta. So P is 31 divided by cos 45, it's coming as 43.84 kilonewton. Now, KL by R of the lacing is equals to 145 at the most, which is mentioned in the code, in the clause 7663. Here, the slenderness ratio KL by R of a lacing member shall not exceed 145. So, we have assumed that, let us take this value 145 to find out the R minimum required. So, R minimum required is coming as 0.32 centimeter or 3.2 centimeter, 3.2 millimeter. So from SP6, let us try with ISA 2024, which is a very small section, but it is having area equals to 1.45 centimeter square and R minimum equals to 0.37 centimeter, which is equals to 3.7 millimeter. Requirement is 3.2 millimeter. So I have taken the higher one, bit higher. So what should be the provided KL by R? It is 0.8. Why you have taken 0.8? Because in lacing member, we can see it is either bolted or welded. If it is bolted, we may take as 0.8, or if it is welded, we may take even less than that. Remember the first clause, we are designing this lacing member as a compression member. The lacing is a axially compression member, and in the design of compression member, we have seen if it is designed as an axially loaded compression member, we can take slenderness ratio 7.7 L to 1 L according to the degree of fixity. So here the degree of fixity is bit lesser, so we have chosen 0.8. If it is welded, we may choose 0.7 it also, 0.7 L also. From table 9C, page 42, where from we used to calculate or interpolate the value of FCD, the permissible compressive stress, by interpolating, we have interpolated between these values. Let's go to the code. So this is the table and the value is 122. So we have to interpolate between 120 and 130 for FY to 50. So the values will be somewhere between these two, 83 and 74. So it is coming as, after interpolation, it's coming as 81.7 MPa. So what should be the AE? The area of the angle, it is 145 millimeter square, was 1.45 centimeter square. The area, we have taken it from SP6, so multiplication of these two will give us the permissible strength, 118.465 kilonewton, which is greater than the force coming on the lacing system or lacing member, which is PL 43.84. Hence, it is okay. Now, we may go for another lecture for to design a batten member, and we will follow it up in the next class. Thank you.